All right, let's get right into it. Have you ever really stopped and wondered how a machine actually learns? Not the science fiction stuff, but the real nitty-gritty theory. Well, today we're going to decode the whole thing, and we're going to frame it like an epic hero's journey. It really all boils down to this one question, doesn't it? How does a machine, a bunch of code, right? How does it actually learn from experience? It feels like magic, but I promise you, there's a beautiful, elegant theory hiding just underneath the surface. And believe it or not, our entire quest to understand this, it all begins with a papaya. Yeah, you heard me right. Stick with me here because this one simple fruit is going to unlock everything for us. So let's set the stage with what we'll call the papaya problem. Picture this. You're on a desert island, and you've got to figure out which papayas are tasty and which are, well, not. The only clues you have are their features, things like their color, their softness, and you only know this from the ones you've already tasted. The mission is to create a rule to predict the taste of any new papaya you find. This brings us to the formal quest. Every machine learning hero, our learner, follows these 4 steps. First, the input. It gets a bunch of training examples, our papayas, that are already labeled tasty or not tasty. Second, it looks at a hypothesis class, which is really just a fancy term for a menu of possible rules it could use. Third, the learning phase. This is where it picks the one rule from that menu that seems to fit the examples best. And finally, the output. It takes that chosen rule and uses it to guess the taste of papayas it's never seen before.
Okay, so our learner has its mission. What's the most straightforward, no-brainer strategy it could possibly take to succeed?
Simple, right? Find a rule that makes absolutely 0 mistakes on the papayas it has already seen. I mean, if a rule explains the past perfectly, it's got to be great for the future, right? Seems kind of foolproof. Now, this very intuitive idea actually has a formal name, empirical risk minimization, or ERM. Empirical risk is just a super fancy way of saying the error on the data you've already looked at. So ERM just means find the rule that minimizes the error on the data you have. Simple as that. And here is where our story gets a little interesting. The strategy seems perfectly logical. It's clean, it's direct. So what could possibly go wrong? Well, let's take a peek at the actual data our learner sees. It gets a few examples, something like what you see in this table. The ERM principle demands that it finds a rule to perfectly separate the tasty from the not tasty ones. No exceptions. It has to get a perfect score. And that right there is the trap. An ERM learner, in its obsession to get a perfect score, can create a rule that is just too perfect for the very specific data it's already seen. It gets lost in the tiny details of the past. And this brings us face to face with the villain of our story, a rule that explains the past perfectly, but is absolutely terrible at predicting the future. This fatal flaw has a name you've probably heard: overfitting. Our learner didn't actually learn the concept, it just memorized the answers to the test. So, this is the critical challenge. Our hero is up against a really powerful enemy. How in the world does our learner defeat the villain of overfitting? It clearly can't just keep trying to perfectly explain the past. It can't do it alone. It needs help. It needs a wise guide, a mentor, to give it some constraints, a little wisdom. And that guide is called inductive bias. So what is inductive bias? It's basically the set of assumptions the learner makes before it even sees one piece of data. Instead of being open to any possible rule in the universe, it restricts its search to a smaller, simpler set of rules. It's like having a built-in preference for simplicity over complexity. Let's make this totally concrete. A really simple but powerful bias could be rectangles only. So instead of allowing our learner to draw some crazy, complicated, squiggly line to separate the good papayas from the bad ones, we tell it, nope, you can only use simple rectangles. This one assumption, this bias, prevents it from creating that ridiculously complex, overfitted rule we were worried about. And this brings us to the fundamental tug-of-war in all of machine learning, the bias-complexity trade-off. On one side, you have simple rules with high bias. Yeah, they might mess a few subtle details, but they tend to generalize really well, making them safer for future predictions. On the other side, you have complex rules with low bias. They fit your training data like a glove, but they are incredibly risky and super prone to overfitting. So by choosing a simpler set of possible rules, by accepting the wisdom from its guide, inductive bias, our learner can finally succeed. It finds a rule that, sure, maybe it's not 100% perfect on the past data, but it's way more reliable for predicting the future. It has defeated the villain, overfitting.
But hold on. This victory brings up an even bigger question. If having the right bias is the secret sauce, well then, isn't there like a master inductive bias? A single universal learning algorithm that's just the best for every single problem out there?
The answer, surprisingly, is a hard no. And the reason why is one of the most profound, important, and kind of humbling laws in all of machine learning theory.
It's called the no free lunch theorem, and what it states is powerful and unequivocal. No single learning algorithm is the best at everything. For any learner you can possibly design, no matter how clever it is, there will always be some task where it fails miserably, while another learner, with a different bias, will knock it out of the park.
This is so central to the whole idea that the source material puts it perfectly. Every learner has to be specified to some task and use some prior knowledge about that task in order to succeed. You just can't have a one-size-fits-all solution.
So, the ultimate lesson from our hero's journey is this. The key to machine learning isn't a search for some mythical master algorithm. The real skill, the art of it, is about matching the right learner's bias to the structure of the right problem. It's all about choosing the right tool for the job. And that leaves us with one final kind of mind-bending question to chew on. If every successful learning algorithm must have a bias, an assumption about the world, just to function, what does that say about the supposedly objective predictions we think we're getting from AI? Something to think